Great. All right, thank you everyone for coming to the Graphs and Matroids seminar. Today we have Nick Brettell speaking, and he's also an editor of the Matroid Union. And I wanted to point out this post that he wrote on the Excluded Miners for GF5 representable Matroids, the small Excluded Miners. All right, thank you, Nick. Go ahead.
Thank you. So I'm also going to talk today about an excluded miner result, but a different excluded miner result for these two particular classes of Matroids. So two regular Matroids and Hydro5 representable Matroids. So we'll see what those are shortly. This is joint work with James Oxley, Charles Semple, and Jeff Whittle. So a bit of background. So a class of Matroids representable over some field F forms a minor closed class. So we can try to characterize this class by finding all of the excluded minors, all of the minor minimal Matroids that are not in the class. This is something that's caught the attention of Matroid theorists since Tutt in 1958, where he found the characterization for binary Matroids. So of course, there's one excluded minor for the class of binary or GF2 representable Matroids. For ternary Matroids, Matroids representable over GF3, Bixby and independently Seymour found there are these 4 excluded minors. And a little bit more recently, Gielan, Gerards and Kapoor found that there are 7 excluded minors for representability over GF4. And of course, the next step in this sequence would be to find the excluded minors for GF5. But this is seen to be a big step up in complexity. I'm not going to talk so much about this problem, but I'm more interested perhaps for this talk in a different class or a different sequence of results about excluded minor characterizations. So this is when we look at the class of Matroids representable over all fields of size at least something. And if that something is 2, then we just get Matroids representable over all fields, known as the regular Matroids. And Tutt showed that there are these 3 excluded minors for regular Matroids. If you look at all Matroids representable over fields of size at least 3, so representable over everything except perhaps GF2, then you get this class of what's known as near regular Matroids. And so Rhiannon Hall, Dylan Mayhew and Stefan van Zwam published proof of the excluded minor characterization for near regular Matroids. There are 10 of these, I think. Yeah. So what would the next step be in this sort of sequence of results? Well, it would be to try to find a characterization for the class of Matroids representable over all fields of size at least 4. And this is something that's still very much open. And it's a problem that I'm quite interested in. So that brings us towards our result. We've been able to find an excluded minor character, or not an excluded minor characterization necessarily, but we've been able to bound the size of excluded minors when we're looking at the class of 2 regular or Hydro5 representable Matroids. So I'll say more specifically what these are in just a moment, but perhaps a more important, more interesting question is why they're of interest at all. So I want to focus on this question of why they're classes that we should put such effort into finding a characterization for. And there's probably a couple of ways I could go about answering this question. One is I could try to convince you that they're interesting classes in their own right, or I could try to convince you that they're useful stepping stones towards answering either of these open problems that we've seen, these GF5 representable characterization or the Matroids representable over all fields of size at least 4 characterization. Okay, so before I get to precisely what 2 regular Matroids are, I want to step back to these results about the characterizations when we're looking at all fields of size at least something. So we've got that the near-regular matroids are a subclass of this class of matroids representable over fields of size at least 4, and regular matroids lie within these both. So if you were to try to find the characterization, find the excluded minors for near-regular matroids, this has already been done, what you can do is start by looking at the characterization for regular matroids, and you'll find either the excluded minors are not near-regular, or perhaps not representable over all fields of size at least 4 as well, or you'll find that they are. And so to understand near-regular matroids, all that you need to worry about was the ones that are near-regular, that have one of those matroids as a minor. So similarly, to understand this class that I'm calling M4, all that we really need to worry about is matroids that have as a minor one of these excluded minors for near-regular matroids. So this is just U25 and U35. All of the other excluded minors for near-regular matroids that are not representable over all fields of size at least 4, these will just carry over and also be excluded minors for M4. Okay, so the takeaway message from this is that we can really focus on matroids with a U25 or U35 minor when we want to understand this class. Okay, so that brings me to partial fields. And for the purposes of this talk, you don't really need to know a lot about partial fields, but I've included the definition here anyway. So partial fields are a more general algebraic structure than just fields. And so we can use them to capture something representability of a partial field can be used to capture something that you can't necessarily capture but when you just look at representability over a field. So you might be able to capture, for example, in fact, you can capture representability over a set of fields. So for any finite set of fields, there exists some partial field such that representability over that partial field precisely corresponds to representability over each field in the set of fields. Okay, so that's useful, but you can also use partial fields to capture some other notions. And we'll see one particular notion having at least a certain number of inequivalent representations over a field in just a moment. In terms of the definition, let me just point out that you can think of a partial field as this pair consisting of your commutative ring R and G, which is a subgroup of the group of units of R, where we have -1 in there. And you can think of this G as specifying what we're allowing as our non-zero subdeterminants in your representations. Okay, so that brings us towards K-regular matroids. And these were introduced by Charles in his thesis. And so there are a few ways you could think about these. The way I like to think about them is if you start off with a uniform matroid of rank 2 that has k plus 3 elements, and you ask yourself, what's the most general partial field that this matroid is representable over? And you can make this idea of most general partial field more precise when you know about universal partial fields. But the idea is that matroid's K-regular if it's representable over this partial field. This partial field corresponding to the most general partial field U2K plus 3 is representable over. So this gives us 0 regular matroids if you're looking at U23, which is just regular matroids, 1 regular matroids, which are near regular matroids if you look at U24, and 2 regular matroids if you look at U25. So if you prefer to think about the partial field definition, what we're saying here is that these are what we're allowing as our non-zero subdeterminants. So if you think about what a representation of U25 would look like up to equivalence, it's going to be something like this, where we need some alpha and beta that are not equal to 1 and not equal to each other. And then we need to allow for the fact that there can be subdeterminants like alpha minus 1 or beta minus 1 or alpha minus beta. Okay, so this is the formal definition of the two regular partial field. Okay, so back to our picture of this hierarchy of matroids representable over all fields of size at least something. We've seen that two regular matroids are an algebraic generalization of these classes of regular and near-regular matroids. But you might initially hope that it would also, that two regular matroids might give you a characterization for M4. But in fact, it turns out that they're a proper subclass of M4. So finding a characterization for this class doesn't yet give us a characterization for M4, but it's a useful step along the way. Okay, so that's two regular matroids. How about these Hydro5 representable matroids? So we're going back into the world of representability over a single field here, in particular this problem of GF5 representable matroids. And so it's known that you can have at most 6 inequivalent representations of a matroid over GF5. And Rudy Pendarving and Stefan van Zwam introduced this hierarchy of Hydro partial fields, where essentially what we're saying is that you're representable over the Hydro I partial field, if and only if you have at least I inequivalent representations over GF5. Okay. So you might think that there's going to be these 6 levels of your Hydro hierarchy from this. But Rudy and Stefan found that, in fact, if you've got at least 5 inequivalent representations over GF5, then you have precisely 6. So there's really 5 layers of this hierarchy to think about. So, so the takeaway from this is that finding an excluded minor characterization for Hydro5 representability, this is going to characterize precisely the matroids that have at least 6 inequivalent representations over GF5. So that's, I think, something interesting to know in its own right. But you might also hope to use it towards attacking this problem of finding the excluded minors for GF5, where you have these 5 layers of the hierarchy. And in theory, you might start by attacking Hydro5, see what the excluded minors are, find where they lie in these next layers of the hierarchy, and build up incrementally in this way. The problem in this sort of approach is that it seems that you're going to be dealing with a huge number of excluded minors once you start getting to the outer layers. But in theory, it's an approach you can take, and it's an approach that you can certainly use in order to compute the excluded minors up to a certain number of elements, which is in the post that Rose was mentioning in the Matroid Union at the moment, if you're interested. Okay, so back to the result. So we've been able to bound the size of the excluded minors for either of these two classes at 17 elements. So a very natural question to ask is this bound good enough for us to actually then find all of the excluded minors? And so first of all, asking this question for two regular matroids, computing the excluded minors for two regular up to a certain number of elements was something Rudy and I looked at when I was doing a postdoc in Eindhoven a couple of years ago. And we're able to compute the excluded minors up to 15 elements. Okay, so there's 16 element and 17 element ones, so potentially the slight gap here. But we can actually say more in our result about matroids that have 16 or 17 elements. We know about matroids on 14 or 15 elements that they'll have as minors. We know that there's only a very small number of these. And it's also possible we've got some ideas on how you could potentially get this bound down a bit further, but there are still details to work out there. even if those don't work, you could potentially just do a computer search on these 16 and 17 element matroids, since we can reduce that search space, but this is not a computation that we've run as yet. So we're pretty optimistic that this will in time lead to a complete characterization of the excluded miners for the class of 2 regular. For Hydro5, there's still perhaps a bit more work to do. I've computed the excluded miners for this class up to 13 elements, so there's a bit more of a gap, but hopefully again with more work we can close that gap. Okay, so that's the result that I want to talk about. So getting to this result has really been quite a long road, and it's involved work of a number of different people. So in this next sort of part of the talk, I want to give an overview of the long road to getting towards this result. So from the viewpoint of 10-ish years ago, if you could see into the future, there were kind of these 4 big problems to solve. So it's possible that I've missed off some things here, but I think that these are the 4 major hurdles that needed to be passed in order to get to this result. So I want to talk a little bit about each of these. So first of all, it's useful to have this connectivity result where we can ensure the existence of a pair of elements that keeps both free connectivity and a miner. So this is this work on detachable pairs that I did with Jeff and Alan. Then once you know that there's such a detachable pair, you can try this fragility approach to bound the size of excluded miners. So you can try to reduce the problem of bounding the size of an excluded miner to bounding the size of matroids in a particular class of matroids known as fragile matroids, and we'll see why they crop up in just a moment. And then you can look at your particular class of fragile matroids. So for the 2 regular and Hydro5 representable, we're interested in U25 fragile matroids. So Ben Clark, Dylan Mayhew, Stefan van Zwam, and Jeff Whittle proved a constructive characterization of this class of matroids. And in particular, I'll talk about the properties of these matroids that were really useful for us in order to bound the size of a fragile matroid that actually appears in an excluded miner. Okay, so this is the 4-stage process. I'll talk a little bit more about each stage. So first of all, this connectivity result. So with Jeff and Alan, as I mentioned, you can view this result as kind of an analog of Seymour's splitter theorem, but rather than just finding a single element that you can delete or contract and keep connectivity in a miner, you're finding a pair of elements. And so it turns out that under a few provisos, you can find such a pair unless you have your miner in, and then you essentially glue on a spike. It's something that looks geometrically like this here. So for a spike, any 2 legs here of the spike form both a 4-element circuit and a 4-element co-circuit, so you're not able to delete or contract any pair. So the provisos are that M must be sufficiently larger than N, otherwise I could have put a number a bit smaller than 10 here, but then some other annoying small structures arise. It's also up to duality, because we're looking for a pair to delete or a pair to contract, and it's up to the delta Y exchange. So this is the operation where we essentially change a 3-element circuit to a 3-element co-circuit, or vice versa. So for our purposes, towards proving excluded miner results, first of all, the delta Y exchange is not a problem for us, because Oxley, Semple, and Vertigan proved that for class of matroids representable over a partial field P, the excluded miners are closed under a delta Y exchange or a Y delta exchange. So this condition isn't a problem for us. The case where we get essentially n with a spike attached, we can also show that these don't appear as excluded minors, so that's not a problem for us. So for all intents and purposes, we're able to say that we can, up to duality, find a pair of elements to delete and keep both free connectivity and a minor. Okay, so I'll call such a pair a delete pair from now on. Okay, so to stage 2. So I want to talk a bit here about this fragility approach to bounding the size of an excluded minor. And so this argument has been used, for example, towards finding excluded minors for GF4 or for near regular. And so some in the Matroid community might have seen this argument a few times, but it's quite important, I think, in order to get an idea of why fragile Matroids crop up. Okay, so first of all, one issue that arises once you're trying to prove an excluded minor characterization and you're looking at fields that have size bigger than 4 or looking at partial fields is that you need some way of dealing with inequivalent representations. So to deal with these, we use this notion of a stabilizer. And what I'm calling a stabilizer here is sometimes referred to as a strong stabilizer. I'm just going to say stabilizer. So what's a stabilizer? It says that once you fix a representation for your stabilizer n, then it uniquely extends. So for any matroid M that's 3 connected and has n as a minor, it uniquely extends, is a unique way to extend from a representation of n to a representation of m. Okay. So that's just for a 3 connected matroid M that has n as a minor. Okay, so now we can say that we have a delete pair AB, and we can, and the idea that we can try to apply is to say, well, start with my matroid M that's an excluded minor and has my stabilizer n as a minor. I'll find some delete pair AB. How can it be that I can put back A and stay representable, or put back B and stay representable, but not both? And this is kind of the idea behind this, this sort of argument. Okay, so more specifically, we can start with a representation of M delete AB, since this has our stabilizer minor. And we can say, let's put B back, or let's put A back, and get column vectors corresponding to each of these. And then you could build up a representation for a matroid that you would get by taking the column corresponding to A and the column corresponding to B. And we'll call this matroid M prime. Okay, so this matroid M prime, it's because it's representable, it's not the same as M, because that was an excluded minor. But if you're to delete A from both matroids, you get the same thing. And if you're to delete B from both matroids, you get the same thing. So we've got something that's behaving a bit like M, even though it's not M. And so since M is not equal to M prime, there's some subdeterminant in this representation that's a witness to that. It certifies the fact that these matroids are not the same. And we also have a stabilizer sitting somewhere in our matroid. And so you can then ask about elements. You could ask yourself, could there be elements that we can delete and keep 3 connectivity and not disturb the stabilizer and not disturb this witness to M being different to M prime? And you can convince yourself that the answer is no. So the picture that we really have is like this here. So what we're doing is getting to a situation where each element that's not in our basis, that's labeling one of these columns here, we can't delete it to keep the minor. And what we're getting for elements that are in the basis, we can't contract them and keep the minor. Up to few subtleties like the fact we've got X, Y, and AB in here that would disturb this subdeterminant, and the fact that it's up to 3 connectivity. But this is getting us towards something that we call being fragile. Okay, so this leads us to the notion of a fragile matroid. And it'll be useful for me to have this concept of flexible elements. So I'll say, first of all, that an element is flexible if you can both delete it and contract it and keep the minor. And then a matroid's fragile if it has no flexible elements. Okay, so back to what we were seeing here, think of these, think of us as being close to being fragile because these elements that weren't in the basis were not contractible, but they could, sorry, not deletable, but they could be contractible. And the elements here not contractible, but they might be deletable. Okay, so that's a fragile matroid. And so this result here is, in a sense, saying that you can reduce this problem of bounding the size of an excluded minor to bounding the size of a fragile matroid. So there are a couple of outcomes. One is that we can straight away just bound the size, so we're happy with this. The other outcome is that you give me a delete pair AB and a matroid M, and I say, well, here's some matroid M prime that's delta Y equivalent to this, and some other potentially delete pair AB, and that's fragile. So as I've stated it here, it's not quite enough for what you'd like in order to argue, in order to bound the size of fragile matroids, due to the fact that you might give me some delete pair and I give you back some other delete pair and say, oh, M's fragile with respect to this other delete pair. But we can actually say a little bit more than this. We can say that if you give me a delete pair AB and M delete AB is not fragile, then we know, first of all, that there are at most 5 flexible elements, and we know about the local structure around these flexible elements. So these pictures aren't important apart from the fact that we can say things, apart from to demonstrate the fact that we can say things like there's a certain triangle involving A or B and certain 5-element co-circuits. So we know a little bit about the local structure around the flexible elements in the case that the M delete AB is not fragile. Okay, so ideally we'd like to completely eliminate this third case, and we can do this, but it relies on the fragile class that you're looking at. So it relies on a certain property of the fragile matroids that you're interested in. And I'll come back to that in a little bit. Okay, so at this point I wanted to illustrate properties of fragile matroids that turn out to be really useful for us. Okay, so these are properties that we really use in the final stage, the stage 4 part of our argument. And so one property of that we'll see that U2-5 fragile matroids have that's really useful for us is this idea of having path width 3. Okay, so what's path width 3? It's saying that you've got some ordering of the elements of your matroid such that if you slice at any point, the partition you get corresponds to something that's 3 separating. Okay, so I'll visualize my matroids with path width 3 as something looking like this here, where with elements like E8 here, what I'm saying is that E8's actually in the closure of both the stuff on the left-hand side and the stuff on the right-hand side. Whereas for an element like E7, this is in the co-closure of the stuff on the left-hand side and the co-closure of the stuff on the right-hand side. Okay, so path width 3 is something that's useful for us. One other thing that's useful for us is to have not many essential elements. So elements of a matroid is essential if neither the deletion nor the contraction keeps the minor. Okay, so For U2-5 fragile matroids, you could easily see that they have at most 5 essential elements, since that's the size of N. But it's good for us if you can show that your class of fragile matroids has not many of these, as few as possible. Okay, so now we actually come to what Clark, Mayhew, Van Zwam, and Whittle showed about these U2-5 fragile matroids. Okay, so they showed that if you've got U2-5 fragile matroid that's in one of these two classes, it's either KRegular or it's Hydro5 representable, and it's sufficiently large, then you get one of two families of things. One of two things can happen. The first possibility is that your matroid is essentially U2-5 with wheels glued on to this U2-5, up to 3 wheels. So here I'm illustrating a U2-5 with a couple of wheels glued on. And the second possibility is that we get something that has path width 3, something with this path-like structure. And they show more than this, but I'm just going to focus on the properties of interest. So for us, it's really just useful that we have this path-like structure. So this first case here, where we have these wheels glued onto U2-5, I didn't mention this so far, but with the proof for excluded minors for GF4, the fragile matroids that crop up in this case are wheels. And these are various reasons why these are nice to deal with. And in some ways, this first outcome is equally good for us. So we're really just concerned with the case where you get something in the second family of objects. However, we can say when we get something with this path structure that there are no essential elements, okay? So every element is either deletable or contractible to keep the minor, but not both. So that's useful for us. And in general, we can also see that in either case, there turns out to be at most 2 essential elements once you're dealing with some fragile thing of size at least 7. Okay, so this brings me to this 4th stage of the argument. So from now on, I'm going to purely be focused on the case where stabilizer is U2-5. We're looking at either KRegular or Hydro5 representable matroids with a U2-5 minor. And I've identified these 2 tasks that we still need to deal with. So the first is, remember that we want, for any delete pair AB, we want to be able to say that we get something fragile when we delete that pair. And the second problem is then once we solve task 1, you want to actually bound the size of a U2-5 fragile matroid, appearing in an excluded minor. Okay, so the first task here, I don't want to say too much about this other than the fact that we get around it using these essential elements. Okay, so in the case that mdelete AB is not fragile, so remember in that case there are these up to 5 flexible elements. And what we can show is that once you get rid of these up to 5 things, you then get something fragile, but it's something fragile that has at least 3 essential elements. Okay, so for U2-5 fragile matroids, this is telling us that once you get rid of these 5 extra things, you're down to something of size at most 7. So this gives us a bound on the size. Okay, so we're able to completely eliminate that annoying case 3 that we saw earlier using this. And the way that we prove this is using the local structure that we obtain when mdelete AB is not fragile. So we know about this local structure, and we have potentially a few different options for delete pairs, and we play off the local structure against each other, and it's quite a painstaking analysis, but we eventually get to this here. So this is why I don't want to really say too much about this proof. So anyway, in either case, it tells us that if M delete AB is not fragile, when we're looking at the case where N is U25, then M, the size of our excluded minor, is bounded at 16 elements. Okay, so to the final sort of part of the argument, how do we bound the size of these U25 fragile matroids in our excluded minor? So there are a few things that we're now able to assume. We're able to assume that for every delete pair, once you delete it, you get something fragile. We can also assume that the M, the excluded minor that we started with, had no triads. Okay, if it had triads, we're going to say, well, let's just y delta these all away until we've got something that has no triads. We can say that we've got no fans, no big wheel-like structures in M delete AB, using a similar idea as what's used to deal with these things for GF4. And as a consequence of this, we can say that fragile matroid M delete AB is always one of these path-like things. So yeah, it's always one of these path-like things. Okay, so these delete pairs are great, but delete triple is even more useful. So a delete triple is precisely what you might think it would be. It's a triple of elements such that when you delete them, you get something 3 connected with the minor. So the first thing I'm going to argue here is the fact that if your matroid has no delete triples, then you've got bounded size. So suppose you've got some matroid that has no delete triples. We know that we've got a delete pair, and we know that the fragile matroid we get after deleting this pair is something with this path-like structure, so it looks like this here. And so what you could do, if you had a long path-like thing like this, we could pick an element, one element from one end, one element from the other end, and something from the middle. And I'm picking elements in such a way that we can ensure that when we delete these elements, we keep the minor, and also that we keep 3 connectivity up to series classes. And this is really a consequence of the fact that we've got something fragile that we can ensure this connectivity condition. Okay, so now we've got M delete AB, E prime, B prime, C prime has this minor and 3 connectivity up to series classes. But we know that the matroid M that we started with has no triads. So if you were to put back A and put back B, these are, because any triads that you might have had in your matroid no longer exist, A or B are blocking these triads, which is going to correspond to blocking series classes, because we've chosen our A prime, B prime, C prime in a way that there are no interactions between these other than ones from your original M delete AB, other than triads from your original M delete AB. So you can argue that M delete A prime, B prime, C prime is 3 connected. And so that tells us that we actually have a delete triple, which is a contradiction. So what we conclude from this is that there's no way that we could actually choose such an A prime, B prime, and C prime. So it must be that our path-like thing wasn't so large after all. And so we are able to bound the size using that. Okay, so that's the case where we have no delete triples. Now we can assume that we have a delete triple. So I've got a matroid M delete A, B, C that's 3 connected with an N minor. And I'm going to continue to assume that we have no triads using the same idea as before. Now M-delete ABC is going to be a fragile matroid, so it's going to be something with this path-like structure. And so here's such a matroid with that path-like structure. And now I can say, well, I could put back A, or I could put back B, or put back C. And in each case, we're still going to have something with this path structure. Okay. So that's telling us a bit about how we could put back an A or B or a C. So it could be that we put back an A as follows. It's lying on the guts, it's in the closure of the left and the closure of the right. Or it could be that we're putting back elements at either of the ends. But essentially, we're forced for one of these three possibilities. And we still have that M has no triads. And so what this is telling us is that putting back A, B, or C is going to have to block any triads that we had in this matroid here. Triads in this matroid don't exist in M. And so these are two conflicting forces in a sense. So you can actually argue that we can't have both of these two possibilities. So M-delete ABC is not something fragile after all, so it's not so big, and we bound the size in that way. Okay, so that's the idea behind our arguments, to show that we can bound the size of these excluded minors for two regular or Hydro5 representable matroids at most 17 elements. Okay, so at this point, I wanted to talk a bit about future directions, what we can, what might be some interesting places to go with this result. So the first place to start is, what does the excluded minor characterization actually look like under this assumption that we have no 16 or 17 element excluded minors cropping up? And then how helpful is this towards actually characterizing the class M4? Okay, so from this work with Rudy, we found that there are these 17 excluded minors for two regular matroids. So remember, this was searching up to 15 elements. And in fact, the largest of them has size 8. So a few things I want to point out. So of particular interest to us are excluded minors that are representable over all fields of size at least 4, those that lie in this class M4. So one of them is this matroid here that you get when you take a non-Fano matroid and relax one more of the circuit hyperplanes. And another one is this matroid that I've called here TQ8 for no apparent reason. And so what this matroid is if you're to take so geometrically, if you take a tetrahedron with 4 points on each of a point on each of the vertices, and then you place a point on each of the faces such that you have symmetry between the points on the faces and the original points. So this is what I've tried to illustrate here. So if you like, the tetrahedron you get from these inner 4 points, for each of the faces of that inner tetrahedron, one of these points lies on that face. So I'm not sure if this matroid's popped up anywhere else that people are aware of. I'd certainly be interested to hear if anyone's aware of it. Okay, so back to where this leaves us for matroids representable over all fields of size at least 4. So our picture now looks like this, where I've just pointed out the matroids that are excluded minors for two regular that are representable over all fields of size at least 4. So up to duality, there's 4 matroids to worry about. The relaxed non-Fano, as I mentioned, the matroid we just saw, U36, and also the matroid that you get from P8 by relaxing one of the two disjoint circuit hyperplanes. Okay, so then you might ask, well, how bad do these classes look? If you look at the matroids in M4 with one of these 4 matroids as a minor, how bad do they look? And for the 2 8-element matroids, so I'm getting to the more speculative part of this talk, by the way. So for these 2 8-element matroids, it seems like you get quite thin classes in that maybe you don't get a lot more than fan extensions, gluing on wheel type things. Whereas for these other 2 matroids, you get something richer, for these other 2 classes, I should say. However, they don't look as rich as, for example, the dyadic non-Fano fragile matroids. So I think that this is not all bad news, although somewhat rich classes, there's still hope of being able to get a good understanding of these. So I think I've got maybe a couple minutes left. So I wanted to talk briefly now about another open problem that's not quite the same, but somewhat related. And this is that we actually don't even know a partial field characterization of this class M4. So what do we know about what the partial field characterization might be? Well, we could start by looking at what we now know about these 2 regular excluded minors. And a natural approach that you could take is you could say, well, what are the universal partial fields for these matroids here? And except U36, for the other 4 matroids, the universal partial field is this K2 partial field that Rudy and Stefan were well aware of. And this corresponds to matroids that are GF4 representable and have at least 2 inequivalent representations over GF5. And so I think for a while they thought that this seemed like a good candidate for characterizing M4, being K2 representable, until they discovered that there's this matroid that's in M4 but only has a unique representation over GF5. So they didn't call this A9, but I'm calling it here A9. And then you could ask, well, what's the universal partial field for this matroid? And maybe that's a good candidate for characterizing M4. And so they conjectured that this partial field P4 characterizes being a member of this class M4. So now I've run some computations that actually look at excluded minors for this class K2, and a few extra things crop up, again with arbitrary names, apart from the fact that these subscripts correspond to the number of elements. And in particular, what you find is that there's one excluded minor for this class that's actually not P4 representable. So you can look at the universal partial field then for this matroid, and can lead you to another possible conjecture for what might characterize representability for M4. So that's this partial field here that I'm conjecturing characterizes M4, and if there is a counterexample, I know that it has at least 14 elements, so it characterizes the class up to 13 elements. Okay, I'll finish there. Thanks for your attention.
Thank you, Nick. We don't do applause because we haven't figured out a good way to do it over Zoom, but thank you. All right, so are there any questions that someone wants to ask while the recording's still going? I'll stop the recording in a few minutes.
Just say thanks, Nick. I'm going to go to class.
See you, Charles.
Cheers.
Yeah, I was wondering, do you think there might be so once you know that you're looking at 2 elements past some sort of structure you understand, like in this case branch width or path width 3,
Yeah.
Do you think maybe we're doing things the wrong way from that point on? Like we know a lot of structure.
Yeah. Possibly.
Put a lot of effort into trying to find a different pair of elements. Like at that
Say
point.
again, sorry?
You put a lot of effort into trying to find a different pair of elements at that point.
So do you mean for this eliminating the case
So
3?
for example, if we knew the excluded minors for path width 3, which
Yeah.
I'm not suggesting that as a solution because you don't want it to go there, but I mean maybe you might want to put some extra connectivity conditions in. There's a lot of excluded minors for path width 3, but if you you know things about excluded minors for representable, so you can throw in some extra conditions. So I've got a matroid with path width at least 3 that also has the enjoys the sort of connectivity structure for an excluded minor. Then maybe we could try to force some other minor a different way and then use that result to find a pair so that we're not in the class.
Yeah. Yeah, that's a good point.
So for example, for GF3, there's a nice proof, a sort of a nice way to finish off the proof for GF3, because you can basically say that if I can delete 2 elements and stay connected, then I'm a fan.
Yeah.
And you don't need to do much in the proof for that. I mean, that comes out really fast in the proof. And then at that point, you can step away and ask about what matroids have this property that if you delete 2 elements and stay connected, you're a fan. And if I contract 2 elements and stay connected, I'm a fan. And you can quite quickly get to the solution from there.
I've got another question, which is that it seems like in a number of cases, you actually get that there are fewer than 17 elements. I'm wondering if you can say, I guess, what the hardest case is, or if you think that 17 is maybe the right answer.
Yeah, so I think there's probably one place where we get 17 here, this no delete triple case, where you can certainly find, I think this one's going to be quite difficult to get down because you can construct a mdelete AB that has 15 elements and doesn't have such a pair A prime, B prime, C prime. So that one seems quite difficult to get down, but it's a very specialized case. I think this is probably the only situation where we actually hit the bound of 17, but there are a number of other places where we hit 16.
Right.
Yeah, does that answer your question?
Yeah, it does. Thank you. All right, I'll go ahead and stop.